Okay, so we have been talking about basically the general properties of detector. We have discussed about this. We have talked about sensitivity, we have talked about response, right? We have talked about energy resolution. Then what if during the charge collection process and creation process the events are not independent? What happens when there is a Fano factor type of stuff? We have talked about it. We have talked about response time and dead time also. Then we have talked about efficiency, different types of efficiency. We have talked about peak to total ratio also. Okay. Now these are the general features or characteristics of detector. Good. Now let us use the detector in actual experiment and see that to make sense of the electronic pulse, you will see, to make sense of it, just having the detector will not help. We will also need something more than just the detector itself, and that is associated electronics. So if this is my detector, then you see the first component that comes after detector, you know what it is? No, of course. What the detector does is, you see, suppose a gamma ray comes over here, okay, and then there is an interaction. As a result of this, charge carriers are produced and then they slowly drift toward the different electrodes and they are connected. Now this time taken by the charge carriers from creation to collection is known as the response time of the detector. This is the property of the detector itself. Now you see, from the beginning of the interaction till the collection, after that what happens? This charge creation and collection, this creates a signal. Okay. Now we have to collect the signal and make sense of it. So the first thing that we have to do is to make sure about the impedance matching. This is a device, right? Very high impedance output. So after that we have to use an amplifier. Why amplifier? So that the signal whose strength is very weak, it can be amplified. But amplifiers, they have very low impedance. Now very high impedance, very low impedance. Okay, so this is amplifier. So what happens is that impedance, I am talking about impedance. Charge is being collected, it is being transferred. But it has got low impedance, it has got high impedance. You know what happens when there is a transfer between very high and very low impedance? This mismatch will cause, what will happen? Tell me. Maximum power transfer theorem, what happens? Power will not be transferred. Remember, maximum power transfer theorem. You have talked about, you have learned about this in graduation, I think. Resistance. But we are talking about impedance here, general complex. So we need to do impedance matching. Otherwise, whatever charge is being created, it will not be transferred effectively. The size will be very much reduced. So what we need is, this is known as pre-amplifier. This is basically an impedance matching device. Now along with the impedance matching between the output of the detector and the input of the amplifier, it also somewhat takes care of the noise present in the output of the detector. Okay, so these are the two main objectives of using the pre-amplifier. Now because this pre-amplifier does impedance matching also, which is the primary function, it is placed very close to the detector, basically on the body of the detector, and then the cable goes forward. So this cable is very short and this cable is comparatively long. okay, to the pre-amplifier. Any questions? So this is basically associated together. They are together kept in a single box. You can think about it over here. Now the next component, Hamalo. Yes. The energy is being transferred, na? As a result of this, electron hole pair or positive negative charge is being created. Overall their numbers is the same, but they are being created, and because of the inherent electric field, they will be drifted to different ends. This is what I am talking about. Now comes the important part. This is sometimes known as linear amplifier, sometimes known as spectroscopic amplifier. So now what are the objectives? So the objective here is to perform impedance matching. This is the primary objective of pre-amplifier. Regarding amplifier, it has got two very important objectives. The first one is, so basically when the output, if you look, you will see something like this, a signal pulse, something like this from here. Okay, the pulse is something like this. Even from the pre-amplifier also, the pulse looks similar to like this. Now notice this signal, what it looks like. This is a typical analog signal, number one. Number two, it is extremely asymmetric, right? Number three, you see this, there are two parts. One is the rise time, the time taken by the pulse to rise. Another is the falling time, the time taken for the pulse to fall. So this is the rise time, peak value, and then this is the time taken. This is the fall time. Now see over here, the rise time and the fall time are very much different. So this is what I mean by saying asymmetric. Okay. Now what I am going to do over here is two things. See, number one, I am going to equilibrate this thing. That means I am going to shape the pulse so that this time reduces. Cannot. Why? I am telling you that we need to reduce this time. I would like you to think about it. Why? No, what I am saying, that is an extreme. Dirac delta type function, that is an extreme. What I am telling you is that for proper spectroscopy, we need to reduce this entire time. Why?
No,
this is what, this is the entire time of taking the pulse. What I am telling you, this time we have to reduce. Why? No, not resolution. Indirectly resolution, but not like that. Why? The reason is that the entire time taken for collecting this pulse, during this time it will be dead. So this is the measure of the dead time, but this is not entirely the complete dead time. This is part of the dead time. And the longer this time is, the longer the detector will not record anything. So this is a very huge loss. In our lab experiments, it hardly matters. Why? Because the source is there and we are also here. We have got entire day to collect the data. But in radioactive ion beam experiments, there 1 hour of beam time, a radioactive ion beam, can cost few crores. So we just cannot afford to lose this time, because losing this time means we are losing counts effectively. The detector will not record anything and we will be losing our precious counts, and maybe one or few counts will amount to few lakhs. It is something like that. It is very costly affair. So what we need to do is optimize the signal so that we can collect as much data as possible in as least as time possible. So, two main primary objectives of amplifier. Number one, pulse shaping. This is known as pulse shaping. So, pulse shaping basically means right now we have got something like this. So, this thing, it has to become something like this, symmetric pulse. You see, the entire time is now much shorter. Now there are two reasons for choosing symmetric pulse. Number one, here you see the time is much shorter. Another thing is it is very much easier to do analysis on a symmetric pulse compared to an asymmetric pulse. So this is pulse shaping. Now this is regarding the x-axis. Another reason is y-axis. That means amplification. So this thing, this will improve. We have to amplify it. Amplifier. What does amplifier does? It just scales up the y-axis, right? Amplifier. So this is the another objective, and this is pulse shaping. So amplifier does two main jobs. One is pulse shaping, another is amplification. Fine. So this is the story till now. So what after that? Okay, as a result of all this, we will be getting lots and lots of pulses and all that. Okay, but how to make sense of it? Now I am going to rub this board. Now, what is happening is that as a result of this, if this is some axis and this is time, then, and this is my detector, say one gamma ray comes, its energy is say 200 kV, and correspondingly after the amplifier, we will see a pulse. No, not this height. Say we will see a pulse of this height, 200 kV, right? This time you see this is symmetric, so this means that this pulse is output from amplifier, not pre-amplifier, not the detector itself. Okay. Next time another gamma ray comes, say 400 kV. Now remember that this 200 kV information is contained in the entire area, entire region covered, right? Now if 400 kV comes, you will see that pulse is something like this. Now there is something interesting. This area is proportional to this height of the pulse. Similarly, again this area is also proportional to the height of the pulse. What I am saying is that 200 kV pulse is this height, then 400 kV is this height. So instead of now talking in terms of area of the entire pulse, what I am going to talk about is just the height of the pulse. Okay, I am going to just talk about the height of the pulse. So this height means 200 kV, this height means 100 kV pulse. Now if if this is a y-axis, then let me do a counting over here. Counting, right? Let me do a counting over here. So let me write it down 1, and this is also 1. This has come once. Now when I am saying these things, this means that they are not appearing at the same time. They are appearing in particular time sets. So there is a window of operation. Some signal comes in. During that time, after its collection, charge collection, the entire system from detector to amplifier, they just do the processing. No more recording of events. So this is the entire date time of the setup. So after this entire date time, the detector is again open to record new data, and during this date time we have collected only this one. Next case we have collected this one. Now suppose after some time another 200 kV gamma ray is absorbed, say after this much amount of time, again 200 kV gamma ray. So what will happen is that we will having now two counts. See? বুঝতে পারছো? So this thing actually, you must be thinking that, sir, it looks very nice, but is it really possible to see this? The answer is yes. And this thing you can see in the oscilloscope. In the oscilloscope, I will show it to you in the next class. You can see these things, but the time what will happen, you will not see the chart like this, there will be gap. So you will see something like this, and after some time there will be no signal. Then again something like this. Then after some time you will see a signal of this height. So this means that there is a 400 kV gamma ray. Now suppose, let me ask you a very interesting question based on oscilloscope. Suppose I have got a source, 137 cesium source, right? Now I am observing the output of the amplifier in oscilloscope, and most of the time I am seeing a pulse of this height, most of the time, but some other times I am seeing pulse of lower heights, a very few times pulse of even higher heights, but most of the time I am seeing this pulse only. Tell me the reason. Why? You see, 137 cesium, what does it emit? Predominantly 662 kV gamma ray, right? So this curve, this corresponds to this 662. But remember, this will have also Compton scattering gamma rays as well. That means 662 kV absorb the detector, but then after Compton scattering they leave. So partial energy will be deposited, and they will correspond to these lower peaks. And then there will be some room background as well, very few compared to this. And you will see some very few large peaks. Now you do an experiment. You take the source very close to the detector. What you will see, this becomes more and more deep. Why? This means there are more and more number of 662 kV gamma rays entering the detector. This is a very nice. Just using oscilloscope you can understand this, and you will be able to understand that this height corresponds to, so in the oscilloscope maybe this is 1.2 volt. Then this 1.2 volt corresponds to 662 kV. You see, you can just do a calibration like this using oscilloscope. Now, what if you take the source quite far away? Then you will see that it will become less deep. Why? Because if you take the source from far away from the detector, less number of gamma rays will enter. So it will become less deep. So this is a very basic experiment using just oscilloscope. বোঝা গেল? একদম বেসিক, আমি তোমাদের সামনে দিন দেখাবো এটা। Okay. So now this is oscilloscope stuff. Good. But we are not going to use oscilloscope to observe. Why? Because the moment it will come, then it will go away. How am I going to record it? I need something more discrete to record it and understand. Right? What I am going to do, look over here. This is my guide. So what I am going to do is, I am going to record only the height. So I am going to record only the height of pulse, and as a result what we will get in is this thing. We will see something like this. So this thing basically is known as pulse height spectra. This spectra means that here most of the time there are pulses of this height, and very less number of times pulses of this height. You understand? তো যখনই তোমরা এক্সপেরিমেন্ট করবে, এক্সপেরিমেন্টে যখন তোমরা দেখবে দিস ইজ ইউর সে 662 137 cesium source, you are doing experiment using sodium iodide detector and you will see something like this. And here this is the energy. What is this? How are you getting this energy? Basically this is pulse height. Understand? This is pulse height and here it will be in terms of volt. But you know that this source emits 662 kV. So this volt will correspond to 662 kV. So you are getting a sort of energy calibration. Next point, you already know that 662 kV where the Compton edge will be. So this is full energy peak and this is the Compton edge. You already know it will be somewhere over here. So these 2 points from the experimental stuff, suppose you are getting this at 5.2 volt. Suppose you are getting this at 4.0 volt, then 5.2 corresponds to 662 and 4.0 corresponds to the Compton edge of 662. So from these 2 points you are able to understand or you are able to calibrate this in terms of energy. So this is how we do experiments. So here I have told you the concept of pulse height spectra. Any questions? Fascinating. I mean, you can do the entire stuff with just oscilloscope as well. And to get more discrete record the data, we have to use the pulse height mode. Now, the story is not complete. Why? The reason is that how are we going to record this pulse height? What I have told you is a theoretical concept that this is pulse height. Fine. Now think about the amplifier output. Large number of pulses are coming and coming and coming. Now how are you going to do a pulse height measurement? Because doing a pulse height measurement means that you have to select a pulse height and then find out how many times the pulse height is coming in a fixed number of time. So how are you going to do that measurement? This means we need one more instrument. So the story is not complete if we just use amplifier. We need one more instrument or electronic part, and that is a discriminator, an electronic unit which will be able to discriminate pulse height against the others. See, this is nature itself. Without discrimination, we will not be able to identify. The thing is that we want to identify, quantify, not just identify, quantify how many times a particular pulse height is coming. So this quantification needs discrimination. Okay, so what we are going to do is use a discriminator. Quantifying pulse height spectra needs discriminator. So what is that? The idea is very simple. Look into this. Look, this is a duster. But instead of a duster, think of it like this. So this is a window, right? Let me move this window. So I have moved this window here, say for 30 seconds. And now observing how many times a pulse is there of this height. No pulse. Next I move it slowly. Next I move it slowly. Next I move it slowly, and then observe the again for same time. So what I am doing is what? This is called scanning the spectrum using 2 discriminators. Here I am using 2 discriminators, and my idea is to measure something in between. Here I will get one count from here, one count from here. There is no count in between. Then again here I will get one count. Okay, so basically I am using a two-level discriminator. And the most basic example of discriminator is single channel analyzer. SCA, single channel analyzer. So what is an SCA? So basically what we have is a lower level discriminator and upper level discriminator. LLD lower level discriminator, ULD upper level discriminator. Now there are many ways of operating this discriminator. I will be talking about one of the simplest mode. It is known as window mode. What we do in window mode, of single channel analyzer, this distance, which is delta E, is kept fixed and only LLD is moved. So this is the discriminator threshold voltage and this one is fixed. So what I am going to do, if this is my spectrum like that, then I am just going to put the discriminator and move it slowly. This part I am going to move it slowly. I am putting it over here for 30 seconds, again slowly moving it and another point for 30 seconds and slowly scanning the spectrum. So this is how we scan the spectrum. And the result is the pulse height spectrum. This is how we measure the pulse height spectrum using the single channel analyzer. Okay, so write it down. Discriminator is always kept on. So the circuit is like this: detector, pre-amplifier, amplifier, and then your discriminator or single channel analyzer here. Now it is always kept on. All the signals coming here, they will go to the single channel analyzer. Now in the experiment you will see, we will put the detector threshold at some value. Say over here, say 1.0 volt. I am taking the data for 30 seconds. Okay. Next I am putting it and delta E is say 0.1 volt. So the next time I am putting it at 1.1 volt. Why? The first one is 1.0, the next one is 1.1. Why? Because when I am taking the data at 1.0 volt, this means the entire range 1.0 to 1.1 is being covered by the window. So this is how I am taking the data. This is what you will do in the lab. So 1.0 volt 30 seconds, 1.1 volt 30 seconds, 1.2 volt 30 seconds and go on. And you see this single channel analyzer, this entire stuff, this is always the range is 0 to 10 volt. Okay, so this is always the range 0 to 10 volt. Now suppose I have just got this 137 cesium source 662. Right? So it will be reasonable to get this entire stuff within 10 volt. Right? So what I am going to do, there is something called gain of the amplifier. Gain of the amplifier. Right? Gain means y-axis. Okay. Gain of the amplifier, by changing it, I can put this 662, this peak, I can put at say 8 volts. And then I will be able to entirely get the spectrum. Now suppose in this spectrum, suppose I have to observe two sources. One is 137 cesium source, another is 60 cobalt. Now 60 cobalt gives you two gamma ray images, 1173, 1332. So this means that if I use this gain, then I will not be able to observe the 1173 and 1332. They will be going out of the 10 volt. So I have to decrease the gain so that I will get 1173 around 9 volts. So this is what we do using the gain. In the lab also you can play with the gain. Normally we set it at a fixed value so that we get this at around 8 volts or so. বোঝা গেল? So there is nothing sacred about it, that it is always happening here. Why is the peak not changing? So let me show you what is meant by the gain of the amplifier. Playing with gain of amplifier. Right. Now suppose my gain is say 1.0. It is also comes in volts. Then if this is 10 volts over here, this is 0 volt. At 1.0 volt, the 662 kV peak. That's just a second. The peak comes at this, say 4 volt, it comes. Now if I put the gain at a higher value, say I am putting it at 2.0 volt, then you will see the peak comes at around 8 volt. Okay, so you see what is happening? This thing is being shifted because of the effect of the gain. Huh? Unitless means? But here in terms, it will be given in terms of volt and doing the changing. We do the change in terms of volt. In the lab, you can play with it also, but this depends on what sources I will give you. Suppose you are asked to do the measurement using just 662 kV gamma ray of 137 cesium source, then this is good enough. But if I ask you to do measurement using 60 cobalt source, then you have to decrease the gain. Why? Because this corresponds to 662 kV and you have to incorporate the 1332 below 10 volts. So you have to decrease the gain.
Gain money itself এখানে তো যে অ্যাম্পলিফায়ার কে আমি যে পাওয়ারটা দিচ্ছি
The entire spectrum আছে তো, the spectrum is being squeezed or expanded. This is the entire matter.
স্যার ওইটা তো আমি নির্ভর করতে পারি যে অ্যাম্পলিফায়ার কতটা পাওয়ার দিচ্ছে তার উপর নির্ভর।
পাওয়ার নয়, অ্যাম্পলিফায়ার ভেতরে একটা সেটিং আছে তার উপর। There is yet another thing that is called pulse shaping time, যেটা তোমাদের বলছিলাম। এই যে pulse shaping যেটা হচ্ছে, the instrument that we have here, they do not have the possibility of seeing the effect of change in the pulse shaping time, but there are modules out there where you can change the pulse shaping time and see the effect on the spectrum. It is possible. So what happens if pulse shaping time is large? Then the peak will be very nice, the resolution will be very good, and means the pulse will be what? Narrower, because you are doing the calculation for a large period of time. So if the pulse shaping time is very small, then the resolution will be bad. This is also important. Pulse shaping time has got effects as well. But again, in the real life experiments, that means I was talking about the RIP, you cannot just take a large pulse shaping time, because that will mean huge loss of data, precious data.